Hi, Chris Good here, and welcome to another lecture for PSYC3530. We're going to be talking about the two-way analysis of variance. So far we've covered the one-way independent groups analysis of variance. We've also covered the repeated measures analysis of variance. This one is on the two-way analysis of variance, and we're only going to talk about the computation of this in terms of independent groups. We are going to talk about a couple of variations where we mix an independent groups and repeated measures design, but for this initial presentation, we're talking mostly about an independent groups two-way analysis of variance. Okay. Two-way analyses of variance are used when you have a complex design. And complex designs are what we call experimental designs where more than one independent variable is being manipulated at a time. We also call complex designs factorial designs. And when we're talking about manipulating more than one independent variable at a time, we call those independent variables factors. So the independent variables in a factorial design are called factors, and the different conditions of the factor are called levels. You can also use these terms when you're discussing a simple design. So we've already talked about numerous examples of experimental designs where an independent variable is manipulated. You could also refer to that independent variable as a factor. For example, we've been discussing the Mozart effect study where listening condition was manipulated as we measured spatial intelligence quotient, spatial IQ. That independent variable of listening condition, what you listen to, could be considered a factor. And the different conditions for that factor, the different levels, we could refer to them that way. So in the simple experimental design for the Mozart effect study, we had one factor, right, one independent variable, with three levels. Complex designs, or factorial designs, when we have multiple independent variables, we're manipulating more than just one thing. Let's take a look at this example. So in the graph in the lower right hand corner here, you see data from a study where two factors, two independent variables, were manipulated. And you can tell what they are by looking at the graph. First of all, along the x-axis, you see that there is a measurement for 0, 10, and 20 on the scale for drug dosage. So drug dosage is one thing that's being manipulated here. But you see two different lines, one indicated by the squares and one by the circles, and they're connected by lines. And the two different lines, the squares line and the circles line, indicate that there are two different types of task. You can tell that just by reading the graph. These are two levels of a second factor. So two things were manipulated here. Participants were asked to do either a simple task or a complex task, and they were taking a drug at a dosage of 0, 10, or 20 milligrams. And we can assume, just for the moment, that 0 means they were taking an appropriate placebo. Now, when we describe a factorial design, like the one that's shown here in the graph, we describe it by indicating the number of levels of each variable. In this case, there are three levels of drug dose, 0, 10, and 20, whatever the units are, I guess milligrams, and two levels of task complexity, a complex task and a simple task. Those are the two levels of the second independent variable. So we would refer to this as a 3x2 factorial design. And we can actually multiply, and the notation is 3x2, and we say it out loud, 3x2. So this is a 3x2 factorial design. It has 6 total conditions. You get that by multiplying 3 times 2. And you can just count them. You can see that there's 6 total data points here. Those indicate mean scores for people within each of these 6 different groups. We have 3 different drug doses doing where people did a complex task. The same 3 drug doses were used when people were doing a simple task, and that's a total of 6 different total conditions. But there's only 2 factors, or independent variables. One of them has 3 levels, that's 3 levels of drug dose, and the other factor has 2 levels. So this is the way that we use the terminology to describe a complex design. There's one more variable that we haven't mentioned yet, and that's the dependent variable. what was measured. Only one dependent variable was measured, and it's very important that you understand that complex designs are those where multiple independent variables might be manipulated, but you're really only measuring one thing. So complex designs involve the manipulation of more than one independent variable, but you'll never see more than one dependent variable that's measured. There are designs where you do measure more than one dependent variable. In fact, they're very common, but you address them with statistics that take into account how they're related. Those are multivariate statistics, and that's beyond the focus of this course. Okay, let me give you one other example, and we'll get into what the statistic actually tells you about. So in this study, what we're measuring, the dependent variable, are the number of errors that somebody makes during a speech. And we're interested in the effect of alcohol on their speech-making ability. So we're going to give half the people who participate in this study a martini before they give their speech. And the other one, we're going to give them a fake martini, a placebo cocktail with a little olive in it and everything. So we're going to ask these, so that's one factor, right? That's one independent variable. And we're going to ask people in both of these groups to address either a large audience or a small audience, because we're also interested in the effect of audience size on the number of errors that they make during the speech. So you're getting either a martini or a placebo cocktail, and once you're in one of those groups, everyone in each group addresses either a large audience or a small audience. So it's independent groups all the way around, and you would describe this design as a 2x2 factorial design, because there's two levels of the first factor, what they were drinking, the drink type, and there's two levels of the second factor, audience size, large and small audience. Okay, I've plotted some hypothetical results of this study in the table 1 as shown on the screen, and these are means. And not only do I have means for each condition, but I have means here in the margins of that average across the means within each one of these cells. So if we look right here at the number 5, this is the average performance of the group who drank a martini. Everybody in the group drank a martini and addressed a large audience. And again, this number 5 is the mean. Down here, the large audience placebo group, that's people who drank the placebo cocktail but were addressing a large audience. This is the average of their performance. Then I've averaged these two averages together in the margins here to get 10, which is the average performance of people in the large audience regardless of what they were drinking. Similarly, I did that for the small audience. And in the other margins over here, I averaged across audience size to get the average number, this number 5 out here in the upper right. This is the average number of errors that people make when they're drinking martini, regardless of the size of the audience that they addressed. 15 is the average number of errors that people make when they're drinking a placebo. And again, yeah, I know it's 15 for both large and small audience. This is the average of those out here in the margin. In fact, we call these the marginal means because we write them out in the margin. So we have 4 total conditions. These are the means for the conditions. These are the means in the margins. And just looking at these data, you can probably tell that it doesn't look like there's much of an effective audience. In fact, in the way these data worked out, their means are exactly the same. But it does look like there's an effect overall of drink type. So there's 2 possible independent variable effects that you're interested in. The effect of your A factor, factor A, which can be drink type in this case, and the effect of factor B, which is audience size. And in a factorial analysis of variance, you end up with an F value that's separate for each one of these. So we'll end up with an F for drink type and an F for audience size. So for every independent variable, every factor, you have an F. And you can compare that F with the critical value to determine whether the overall effect, or what we're going to call the main effect, is significant. And here it looks like, even before we get the F values, it looks like the F for the audience size factor isn't going to be significant, that there's not going to be an effect of audience size when you ignore the drink type. But it does look like there may be a significant effect of drink type when you ignore audience size. But, as you see at the bottom, it says the factorial analysis of variance in a two-factor, a two-way analysis of variance, you end up with 3 values for f. What's that third value? Well, it's actually for the interaction of these two variables. And the interaction is something that's kind of hard to explain, but I think that you'll know it when you see it. So we're going to practice looking at main effects, that is, overall effects of individual factors and the way that they interact with each other. But first, I want to talk about the first two f's that we got and how we might get them. Now, you should understand that I'm not going to ask you to compute any of these values for f, but I do want you to understand how they are computed. I'm not going to ask you to do it, but I am going to ask you a couple of questions on how it is done. Okay. So again, we're looking at 2 factors, only this time one of them is a subject variable. We still use the independent group's statistics to deal with subject variables, but we're kind of limited in the conclusions that we can draw. Here, we're looking at data from, again, this is the Mozart effect study, but now we're adding a second factor to it, which is gender. So we're going to ask people whether they identify as men or women, and then we're going to we're going to treat that as an independent variable, even though we know it's completely not independent. But we're going to treat that as a factor with 2 levels. Same 3 levels of the other factor. In this case, it's the B factor. And those are the 3 different listening conditions for the Mozart study, Mozart relaxation and silence. We're going to measure, same thing, spatial IQ. And in this table, you can see that we've got 6 different cells. This is a 3 listening condition by 2 gender factorial design. That's how we would describe it. You can say it the other way. You can say it's 2 by 3, but you have to be consistent in your naming. So if you say it's a 2 by 3 design, it's a 2 by 3 factorial design examining the effects of gender, which is the 2, and listening condition, which is the 3. So as long as you're sort of parallel in your sentence construction when you're talking about it, that's totally fine. So in each one of these cells, I have 3 data points. I have the mean of the 3 data points. I have the t, the totals for each one of these data points. I have the sums of squares for each one of these data points, each one of these cells. Over in the margin over here, I have the n, overall n of 18 scores, the overall g, the total of all the scores, and the sum of all the scores squared, the sum of all the squared scores. And if I could write out in the margins here, I could also write t's for each one of the columns, right? So in the Mozart condition, we have a t for this column, a t for the relaxation column, and a t for the silence column. I also can do t's in the margin over here for men and women. And we can use those to calculate sums of squares for each factor separately. So all of the other sums of squares apply in the same way that they always have. Our total sum of squares is the sum of x squared minus g squared over n, right? It's the sum of x squared minus the square of the sum of x divided by n. And that total sums of squares can be broken into sum of squares within treatments. That's the sum of squares for each treatment. And the sum of squares between treatments. And when this says the sum of t squared over n minus g squared over n, I'm going to go back a slide now. It's the sum of the t's in each one of these cells, right? This is the sum of squares sort of between all 6 of these different treatment groups, or among all 6 of these different treatment groups. But then we have 2 new sums of squares that we have to talk about. There's sum of squares for the A factor. And in this example, sum of squares for A is the sum of t squared over n just for the rows. So it's the sum of squares, sorry, it's the sum of this t squared, the t for men squared, divided by its n, right? Which is 3, 6, 9, plus this squared, 9e squared for women, divided by 3, 6, 9 total scores in the rows, right? Minus g squared over n. That's sum of squares for A. Now again, I don't want you to calculate this, but I do want you to understand where these sums of squares are coming from. Similarly, we can come up with a separate sum of squares for the B factor. We can come up with a sum of squares just for listening condition by totaling across these two rows for Mozart for a sum of 18, totaling across the two rows for relaxation for a sum of 54, and totaling across these two rows in the silence column for a sum of 72, right? And we would square each one of those totals divided by its n, right? So the n here is 6 for Mozart, 18 squared over 6, plus 54 squared over 6 scores in the relaxation column, plus 72 squared over 6 for the silence column. And what we'd end up with is a sum of squares for B. Okay. There's a third sum of squares. And so each one of these has its own degrees of freedom. Each one of them has a mean square that's just the sum of squares divided by its degrees of freedom. But there's a third sum of squares that we're going to get by subtraction. So if you add it up, the SS between should partition out into the sum of squares for A plus the sum of squares for B, but you'll find that there's sometimes a little bit left over, and that's the sum of squares for the interaction. Alright, so we've already gone through the sum of squares for A, that's the one at the top. It's the t squared for the rows divided by the n for the rows minus g squared over n. We've already been through the sum of squares equation for sum of squares B, that's the t squared for the columns divided by n for the columns minus g squared over n. And the degrees of freedom are very simple. Degrees of freedom for the variable across the rows is the number of rows minus 1. The degrees of freedom for the variable that's distributed across the columns, in this case it's listening condition, is the number of columns minus 1. So df for A is 1 because it's 2 rows minus 1, 2 men and women, right? That's 2 minus 1 is 1. dfb is 2 because it's the number of columns, 3 listening conditions, minus 1 equals 2. What we haven't gotten to is sum of squares for the interaction. We write it AXB. The sum of squares for the interaction is what's left over after you subtract the sum of squares for A and the sum of squares for B over sum of squares between treatments. I'm going to go back a slide now. How did we get sum of squares between treatments? Well, it's the sum of the t squares over n, back one more slide, where t squares are the t's in each cell here. All 6 of these cells, so for this one, this first Mozart for men listening to Mozart would be 9 squared over the number of scores, which is 3, plus the men in relaxation, 18 squared over the number of scores, which is 3, plus 27 squared over 3 scores, plus the women Mozart, that's 9 squared over 3, 36 squared over 3, 45 squared over 3, and you sum all those up to get SS between. Then you subtract sum of squares A and sum of squares B, and what you're left with is the interaction sum of squares. You'll need to divide it by the degrees of freedom for the interaction, and that's the df between treatments, where that's the total number of conditions that you have minus 1. How many treatments do we have in total? Well, there's 6. Even though being a man or a woman isn't really a treatment, at least not ethically, we do have 6 different total conditions, right? If we go back to the data, there's men Mozart, men relaxation, men silence. Women Mozart, women relaxation, women silence. So there's 6 total cells, so we have a degrees of freedom for between treatments, even though gender isn't a treatment, of 5. So it's 6 minus 1 is 5. Okay. We have 3 different mean squares then that we calculate. A mean squared for A, just the sum of squares over degrees of freedom. A mean squared for the B factor, which is listening condition here. A was gender. And finally, a mean squared for the interaction. That's the sum of squares for the interaction that we got from subtraction, divided by the degrees of freedom for the interaction, which we follow the same pattern. If the sum of squares is between minus A minus B, then the degrees of freedom is between minus A minus B. Now, finally, these are the F values. Okay, so F for A is mean squared A over MS within. How do we get MS within? Let me go back to the data. We got MS within by getting SS within treatments. That's sum of squares for Mozart men, and for relaxation men, and for silence men, and for women Mozart, and for women relaxation, and for women silence. Those sums of squares all added up. This is the sum of squares in each treatment added up. That's how we got the error term for this F, MS within. That's so for A, it's MSA over MS within. For B, the F for B is MSB over MS within. And the F for the interaction is MS for the interaction divided by MS within. Okay, well, the main effects, that is the F for the main effect of A, or the F for the main effect of gender in this case, is pretty simple. That's just asking whether there's a difference between men and women. The F test for the main effect of B, main effect of listening condition, regardless of whether you're a man or a woman, that's pretty easy to interpret too. That's just the regular ANOVA that we've been doing. What on earth does the interaction say? Well, all the F will do is tell us whether we have a significant interaction or not. And when you have a significant interaction, what that means is, and don't worry if you don't get this the first time around, because I'm going to say it a lot of different ways and give you a lot of different examples until we're all on the same page. What a significant interaction means is that the effects of one factor depend on the other factor. In this case, our two factors are gender and a listening condition. And if we did calculate F for the interaction and found a significant interaction, it would mean that either the effects of listening condition depend on gender, or it's really saying the same thing, that the effects of gender depend on the listening condition. So let's imagine a case where you do get an advantage listening to Mozart, right? So your IQ scores are higher under Mozart, but only if you're a woman. That would be one interpretation of a significant interaction. And how would we know? We'd have to look at the data. So I'm going to give you a couple more examples of this. Let's go back to the Martini study, where we're looking at a 2x2 factorial design that's testing for effects of drink type and audience size on the number of errors one makes when given a speech. So here is one way that those results could have come out. It's not the way that I just showed you in the table of data earlier before, but it could have happened like this, where if you're addressing a large audience, then it doesn't matter whether you got the Martini or the placebo, you make a bunch of errors. You make a bunch of errors addressing a small audience too, unless you've had a Martini. If you've had a Martini, the number of errors that you make to a small audience decreases. This doesn't work, however, in front of a large audience. And this is a good example of an interaction. So we would have to compute F to know for sure whether this interaction is significant or not. But if it is, we would understand that the effects of the drink type depend on whether you're addressing a large or a small audience. And this is a case where you only see an effect of Martini when addressing a small audience, and you don't see an effect, sorry, let me say that a different way. The effect of drink type is seen only when addressing a small audience. So Martinis only decrease errors in front of a small audience, and they don't decrease it compared to the placebo when you're in front of a large audience. Okay, next slide. One more example of main effects of interaction, main effects and interactions. So back to the simple and complex task and drug dosage. We have an interaction here too, because the effects of the drugs seem to be different depending on the other factor. What is the other factor? It's the type of task you are given. That factor has two levels, the simple and complex. And the effects of the drug seem to decrease completion time when you're doing a simple task. But it seems like as you increase the drug dose, your completion time increases when you're doing a complex task. So once again, the effects of one factor, the dose of the drug, depend on the other factor, task complexity. In fact, in this case, this is a situation where the effects of one factor are opposite depending on which level of the other factor that you're testing under. We'll discuss this more in class. Let me show you one last slide, and this is the output file that you would get from a computer program like SPSS, and there's many others that output results of analysis of variance, of a two-way analysis of variance in the form of a source table that looks like this. And I know there's a lot of decimal places and it looks really complicated, but the table is organized pretty simply, and it's organized like this. First, it tells you the source of all of these different statistics. And this is a report, let me go back one slide, of these data, of the completion time data. This is a report analyzing basically the results of this study. All right, so the source of T is indicating the task complexity source. There's 1 degree of freedom because there were 2 different types of task complexity. This is the sum of squares for that factor, that first factor of task complexity, and this is the mean square for task complexity. How come they're the same number? Because mean square is sum of squares over degrees of freedom, and this sum of squares is divided by this degrees of freedom, and so you end up with the same number. It also tells you the F value that you get when you divide the mean squared for this first factor that has 2 levels, because degrees of freedom are 1, by the mean squared for the error term, which is MS within treatments, and it's listed down here. It has 42 degrees of freedom. This is the sum of squares, this is the mean square, and this is the F, which is this mean square divided by error. Next line down, you see D. This is drug dose. It has 2 degrees of freedom because there were 3 different levels of drug dose. We have the sum of squares that's given, calculated by the computer program. The mean square is just the sum of squares divided by degrees of freedom. And the F is the mean square for that factor divided by the mean squared for the error term, which again is within treatment's mean square. Finally, we have TD. That's T by D. That's the interaction between T and D. It has 2 degrees of freedom too because, let's see, how can we do this? There were how many total groups here? There were 6 total groups, right? And that means that there's 5 degrees of freedom between these 6 treatment types, minus 1 degree of freedom for the task factor, that's 4, minus 2 more degrees of freedom for the drug factor, leaves us with 2 degrees of freedom for the interaction. We have a sum of squares for that interaction and a mean square, which we get by dividing the sum of squares by the degrees of freedom. And we have an F value that we get by dividing the mean square for the interaction by what? By the error term, the within treatment's mean square. Finally, we have one column over here all the way on the right, which is p-value. So you'll notice that it doesn't say p is later or less than anything. It gives you a specific value for p. At the top, this first one, it gives you 0. Of course, it's not actually 0. It just, p is so small that there's not enough decimals on the screen to tell you exactly what p is. So if you were reporting this, you'd have to say that p is less than the lowest number that can be described by the lowest non-zero number that you could describe here. So we'd have to say that p is less than 0.001 in this case. But here we can report that p is actually equal to 0.841, and finally on the bottom, p is equal to 0.006. And as you might guess, p here is lower than a reasonable alpha for which effects? Well, first for the main effect of treatment type, task complexity, and for the interaction as well, and the effect of the drug dose is not significant. And we'll talk more about why that makes sense based on the data in the graph when we meet together in class. Thanks, and I'll see you next time.